start it again. So this particular session is essentially going to deal with the coupling with thermodynamic databases, and I will essentially showcase these strategies that we use for coupling to databases, both encrypted ones and the open databases. And I will illustrate it by using the grand potential solver, but I will also show test cases for the other that have been performed with the other solvers as well. They have the same scheme. The strategy remains the same, except that the solvers are different. OK, let's get started. This is the phase field model. You start with a functional. You have a gradient energy term and the potential energy term. Together, they typically give you what is known as the diffuse interface that is described in this part over here. So you have a defined interface width. And if you were to integrate using this equilibrium profile in the functional, you will essentially get the interfacial energy. Now, the idea is if you want to have phase transition, you need to move this interface with a given defined velocity. And that's what this driving force term does. And the next few parts of the next few slides will essentially deal with how you incorporate this driving force into the phase field simulation. So let's say you want to do solidification of pure materials. The way to do this would be to incorporate this using the classical way. So the difference of the free energies is the driving force, Fst minus Flt. So this is also illustrated in this small figure that is given over here, where you have Fs of t and Fl of t, which are equal at Tm. And then for a small undercooling, you have a difference which gives rise to the driving force for the solidification process. OK. On the other hand, T greater than Tm, you would have this being negative, which would result in the solid melting. So this essentially you can derive the evolution equations for phi and the temperature, which is the dependent variable over here, you as a function of time using the classical evolution equations which follow from the decrease of the you can from the variational derivative of the functional. OK, now this is for solidification of pure materials, and what we really want to extend it is to any multi-component alloy. So we can extend it the same way. There have been several attempts to do this, and the typical strategies that people utilize are models of type 2 and models of type 3, and extensions of this, which is the grand potential model, which I'm going to show now. So the idea behind the grand potential model is precisely that you transform this information from a f of c, that is the change of free energy as a function of composition. Instead of using this information, you utilize the Legendre transform of this free energy, which is telling you what is this intercept variation as a function of the slope of this line. So this is essentially the grand potential density that I'm going to call and define it in this form. This is the Legendre transform of f of c, and this is essentially what the transformation has happened by changing from c to the variation of the slope, but the actual information essentially remains the same. OK, so physically, whatever information I wanted to give with respect to f of the change in free energy with respect to c can also be captured by plotting what is the change in the intercept as a function of the slope. OK, so they are equivalent ways of treating the same problem. The advantage, however, is if you were to do this way, you get rid of some of the nasty difficulties which arise because of f of c, particularly to do with interface excess at the interface, and you get to control and decouple, control the interface properties and decouple it from the free energy thermodynamics. So all of this is detailed quite heavily in these two papers, but so I will not go there, except that only model of the story I want you to take is that using such a formulation, you are able to do quantitative microstructure simulations effectively and efficiently. OK. OK, the idea behind this is actually very simple. So if you were to look at this, this is the equilibrium between a solid and the liquid, which is illustrated by the common tangent construction. So you have this psi equilibrium being denoted by this pink point over here, and that would translate to this temperature versus composition curve, where you have these two as the equilibrium points. Now the same information, if you were to plot the psi of mu plot, so you were to, let's say, find the equivalence between f of c and psi of mu, this same information would be transformed to this, where you are having intersection of the psi plots at a given mu, which is the mu equilibrium. So this would be in direct analogy to what you had for the pure material case, where you had fs and fl, where t at a given tm you would have equilibrium, and here you would have psi equilibrium, psi being equal at a given mu. So the corresponding thing for when delta psi, when you have a driving force, would be when mu is different from mu equilibrium, or when the slope is different from this nice value which gives you the common tangent. Anybody spoke? It would essentially give you a difference between the psi s and psi l that would correspond to the driving force, which is again analogous to what you have delta F for the pure material case. So essentially what you see is that it is a direct extension of what you had for the pure materials, and therefore analogously just develops from there. And that's the elegance that we utilize for the grand potential description. OK, so now the rest of the lecture would be how I incorporate this driving force using the couple coupling to thermodynamic databases. So I will skip all of this because this can directly come. So I'll directly go to strategies for thermodynamic coupling. So this I have borrowed one slide from Funny because essentially this is what we are have done. So if you look at thermodynamic databases, you have two ways you can input two types of databases available in the market. So you have encrypted databases. So these are proprietary databases made from that can be got from Pandat and Thermocalc. They are owners and makers of these databases. So they will only give you things that you can calculate with the database, but you cannot see the database with all its functions. OK, so that means the functions are not available to you, but you can evaluate properties that you need thermodynamically using these encrypted databases. And those calculations can be done using softwares like Thermocalc and Pandat, who are also makers of the databases. And the extraction of interfaces can happen through TC API and Pan API. So TC API would be something like TC Python, and Pan API would be Pan Engine or Pan Python, depending on what you have. And these would be directly what we want to input. These calculations will be directly input into parameters for phase field, which will be essentially for the MicroSim solver. The way it is typically done in commercial softwares is they have an interface directly with the Thermocalc. So because they have the proprietary information already available, Micros is directly linked with Thermocalc. So they have the proprietary interface already done. So all they need to do is to write a TQ interface which actually works on the actual functions written in the TDB. This extraction step is not necessary. OK, but we have to do this because we do not have the encrypted databases. The other way is for databases which are openly available. So one of these examples which I will show. So for unencrypted databases, you can again get the information from Python tools which extract these functions in a way using. So this is the data writer tool that is there part of MicroSim, which talks to PyCalFed and uses SymPy to convert the expressions that are read from the databases into functions that can be evaluated in MicroSim. OK, and these are again input into PF for the MicroSim simulation. So this is the workflow we'll have. We can treat both encrypted and unencrypted databases, but the workflow are different given the information that can come from each of them. OK, so this is what I will illustrate to you in the next few slides. So let's talk about OpenTDBs first. In OpenTDBs, so you have seen there is the in file that we will also see now. In an in file, there is a key called function F, and this function F2 in the in file for all solvers essentially corresponds to talking to TDBs exactly. OK, and we are presently talking to TDBs without sublattices. In future, we will also have TDBs which can talk to which have sublattices as well. So on the left of the TDB is how a TDB function, a TDB file looks like. You have several of these functions which are codified as text files. OK, this is how it looks like. And what PyCalFed or the this particular tool does, which is gDataWriter.py, it converts this particular in file into functions on the right hand side that you see over here. OK, so this parser is part of PyCalFed and it is done using SymPy. All right. So these functions on the right hand side, which you see, are essentially read into the data in the solver, and you can perform thermodynamic calculations with this. OK. The other strategy is so one of the issues, I will just talk briefly about this. One of the issues that was previously thought about in the phase field literature is essentially that for performing the Legendre transform, one needs this composition as a function of the chemical potential needed. That's one of the essential parts of the Legendre transform. OK, now if this cannot be performed, typically you cannot do the Legendre transform, and therefore the psi cannot be made. However, the point over here is even if you have non-convex free energies, where the problem arises, this C of mu can actually be done locally using GSL libraries. So you essentially tell the solver that you are not going to deviate all the way to all parts of the mu landscape, but you're only going to restrict in the space where your curve is convex, and thereby the C of mu can be numerically inverted using the GSL libraries. And this is what we do. So even functions which are non-convex, that is thermodynamic functions which are non-convex, are possible to get to incorporate to be incorporated into our solver. Okay, so I will show you examples of this. So the way we do it, we solve both the composition and the mu update, and this is a little bit different from how the KKS update is done. In the KKS update, this mu comes from a Newton iteration. Here we are not going to do that. We are essentially getting this from a transformation of this equation, rather a linearization of this equation to a transformation into this equation, which allows you a mu update, which is seamless, which is quite efficient numerically in comparison to the Newton iteration. However, there is a nonlinear iterator required for the C of mu evaluation because this is a nonlinear equation. OK, so that's what the changes in the solver are due to. So the second thing is, if you want to, as you will find over here, this particular evaluation of C of mu, because it's done through a nonlinear solver, is quite numerically intensive. So one of the strategies we have adopted is also to have approximations of the free energies, which are actually read in from the TDBs, and construction of simpler functions, which we are going to claim are going to give you the same thermodynamics as the original exact coupling. OK, and this is called this can be achieved through function f3 in the infile. The idea is as follows. You write down the f of c as a parabolic extension, a multi-component parabolic extension, where aij alphas are essentially the related to the second derivative of the free energies, which are coming here. So these are typically the Hessian of the free energy matrix, which in most TC API and Pan API thermodynamic softwares, this can be extracted quite readily. OK, so aij alpha is something that I can relate directly to a TDB by directly calculating this matrix out of the thermodynamic database. And these components B, Ga, and C alpha can be derived from formulas of this type, which are illustrated over here, which ensure that the phase coexistence boundary that is originally there in the phase diagram is getting reproduced in your phase field model as well. So ideally, so what you're taking is the thermodynamic properties which are determined by the Hessian, as well as the phase coexistence boundaries are getting mapped as a function of temperature exactly. So the temperature dependence is also treated in through the calculation of the slopes. These slopes are calculated, slopes of these phase boundaries. These are calculated from the thermodynamic information that you already input in the TDBs. So you don't have to input them. They get calculated internally in the solver. OK, so this is the function f3, which is an alternate to the exact coupling. The exact coupling, as I will show, is slower. OK, the other way is for encrypted databases where you do not have any information available for the functions. So this is we are doing through function f4, and the function f4 reads in files of the type that are sitting over here. These are extracted from the TDBs, from calculations from TDBs. So you do not have the functions, but you can have calculations of the functions. OK, so what is evaluated from them is for temperatures, you evaluate the phase coexistence lines of one phase in equilibrium with the parent phase. OK, so you have to choose one parent phase and equilibrium of all the solid phases that you want to consider, or all the precipitate phase that you want to consider in equilibrium with the matrix phase. So for a binary, there will be only two columns because there are only two components. For a ternary, you will have corresponding two columns for the solid phase and two columns for the liquid phase. OK, so this is how the composition file that needs to be extracted from the TC API or Pan API. Similarly, this is the Hessian matrix, where for the temperatures, you can extract the d square g by d c square directly from the info. So this is all that will be read in from the databases through the Pan API and TC API, and these will be used to calculate A, B, and C such that the phase coexistence boundaries get reproduced in the same manner. OK. OK, so that's essentially the strategy, and I will show you and convince you that these strategies essentially give you equivalent results, and thereby you can choose the most efficient way of doing things. OK, so let me show you a test case. This is a simulation set up for a benchmark. So we have done a single dendrite calculation, which is of this type, which is undercooled. So the melting point of the alloy that I have chosen is 870 Kelvin. I have tested two different undercoolings, 4 Kelvin and 13 Kelvin. The dynamics will be diffusion control, that means no interface kinetics, and the strength of anisotropy is 0.01. OK, so the infiles for this are available in the examples infiles repository that is already shared with you. OK, so this is the simulation benchmark I will utilize for comparing between F2, F3, and F4, which are the three variants of doing the same thing. OK. So let's go ahead. So this is the comparative study. All right. This is the delta T is equal to 4 Kelvin. The two blue lines essentially corresponding to the binary to the F3, which is the parabolic with where the open TDB constructions are possible. That means you can read in the TDB and evaluate the second derivatives through the functions that are there in the infile, and function F4 where the functions are not available with you, but you can evaluate the second derivatives through the PAN API and TC API and use them in the software. So you see that these are fairly similar, and the red line is the exact coupling, which means you are using the exact, you're not making any approximations with respect to the free energies, and you are doing the calculation. So delta T is equal to 4 Kelvin. You see the shapes are relatively overlapping, and there are some small differences that come in over here, but I will convince you these differences are actually small, because if you have a look at the velocity plots, that is velocity as a function of time, this is what happens at 4 Kelvin. You have difficulty differentiating between the plots, which is both at 4 Kelvin and 13 Kelvin. The maximum differences we saw were of the order of 5%, which for an industrial perspective or a typical academic perspective is rather small. So now the question is, which is the most efficient way of doing the stuff? The question is, and that can be addressed by seeing the computing times that are required for each of these evaluations. So I'll give you typical run times for the exact solver. This is done on our National Supercomputing Mission machine, which is the Parampara Vega. We use 960 CPUs. The exact solver, which is function F2, requires 3.5 hours for the entire evaluation. OK, the parabolic solvers, which is F3 and F4, they require 30 minutes. Now the decision is obvious. If the differences of that order, you typically would choose the faster option because it gives you most efficient results. And there my contention is essentially for most computations that are necessary for applications of the type that metallurgists are interested in, one can just stick to the simpler approximations that allows us to even use encrypted information in a easy manner. OK, I will also convince you that in the plots that you see, there are several different test studies that have been done. We have compared obviously the functions. We have compared against different machines. Also, we have compared against different solvers. So you see OpenCL implementation as well as OpenFOAM implementations. OK, so there's a multiplex comparison that I'm trying to present over here. And my point over here is the following. The salient points. We have compared parabolic versus exact, as we have done. We have compared the solvers are different. So you are comparing double well in some of the solvers versus obstacle potential. So your potentials are different. You are comparing finite difference approaches versus finite volume. Finite difference are the OpenCL approaches as well as the OpenCL and the grand potential approaches, whereas finite volume is the OpenFOAM approach. Implicit solvers were used for OpenFOAM. Explicit solvers were used for finite difference. KKS was used for the OpenCL solvers. Grand potential was used for the MPI solvers, and the implementations were different. But even with these differences, you have matches of the type that we have. So essentially, the point over here is, if the implementation of each of them is done correctly, you can derive the same physics between each of the solvers. The critical point over here is the physics of the model construction needs to be same. And therefore, if they are done similarly, the implementation, the choice of the scheme, the errors that you get are minor, are rather small for any consequence to that what you want to derive information out of. So that's essentially the story that I wanted to tell about. And the solidification is not the only thing that can be presented. You can also do precipitation reactions. So for example, this is Solvus 500, which was undercooled to 400 Kelvin. The size domain is of 0.25 micrometer cube. So you can have a look at the simulation over here, which will start to coarsen very quickly. So you see particles or precipitates going away and coarsening happening. So this is done again with thermodynamic coupling with function F3. And what I wanted to tell you was what pass on is that the information workflow can work with TDBs very efficiently. OK, let me speed up so that you can see coarsening very large. OK, so I hope I have convinced you that we can do real alloys quite nicely. And therefore now what we will in the next few minutes, what we are going to do is to live do this with ourselves, right? So that you can see how it's being done. So what is this? Let's go there. Let's open a. So if people have already installed stuff on their computers, you can actually start to run as I'm doing. I will tell you where to get the in files from, and you just have to follow me. All right. OK, so this is how it opens. So what I'm going to do is to start simple. I'm going to recreate the single dendrite growth problem that I showed you. So I'm going to import in file. Now this in file, you can download it from in the repository. There's a folder example in files, and it has the same name that I'm going to use now. So you can just go to the repository and in the example in files, copy the same in file that I'm copying over here. OK. So let's go here. So just copy this guy, input TDB new. All right. So you have to just copy this, import this in file, and where all the necessary parameters are already loaded in. So what I will change is, in the interest of the small simulation domain that we can access on this small machine, I will reduce it down to a manageable number. And then go ahead, phase components. So these are already there from the in file. If you want to change them, you can do. It's alpha and liquid. These are the proxy names given for the thermodynamic phases that are already there. OK, so we are OK with this, so we can stay with them. The component names are also read in from the in file. So they are aluminium and zinc. The things get solved in for the K-1 phases that are incorporated. So aluminium is there over here. Second, then you go to number of time steps. So we'll run it for small number of time steps so that we can say 1000. Restart is not required. We are starting from new. So next. OK, here are where the properties get input. So we are using a diagonal matrix. For the alpha is the solid phase, so that's why it's 0. Similarly, you have liquid. Liquid is 1e minus 9. OK, which is the typical solidification diffusivity that you would have in the liquid for in the solid phase. If you have exact values, you can also input those values. OK, so then you can go to gammas. This will prompt to you how many gammas are required. So presently there's only one interface, so you have just one gamma to input. In fact, so we are choosing function F3 here. It's faster, and just as I've convinced you. And here is where you essentially utilize the thermo phases. That means they give the number of the thermodynamic phases in the system. That means these are the real physical phases that you are going to have in the system that you are trying to solidify. So these are 2 in number here because we have FCC and liquid from the phase diagram. OK. Similarly, so in just to keep you in sync, I will just navigate to the this is the phase diagram. OK. So you see this is the FCC phase. This is the HC liquid, and we are doing a composition which is over here 870. OK, so the 2 phases in equilibrium over here, which I'm going to choose, is FCC and liquid. Right. So let's go back. So I'm going to choose the TDB, which is aluminium zinc, because this is where I'm going to read the information from. FCC A1 and liquid, FCC, and this is essentially telling you the phase map. What is this phase map? Phase map tells you these are the thermodynamic phases. You had inputted 2 phases, alpha and liquid, before, which are your phase components here. You see these are the phases you put in, alpha and liquid, right? So what is alpha corresponding to thermodynamically and what does liquid correspond to thermodynamically is what is given over here. So alpha corresponds to FCC A1 and beta corresponds to liquid. So that's the phase map that you need to provide. You need to tell alpha and liquid are what thermodynamically. So once you have given that, then you have to give phase compositions, and these phase compositions are essentially the equilibrium compositions at the alloy of interest. So you have to go to the alloy composition, and these properties, where do you get it from? if you are using PyCalphate, you can directly print out the values for that particular composition directly. And you can then fill the composition corresponding to the equilibrium and give a stimuli to your simulation by giving an undercooling. OK, the other way of doing it is just to give a supersaturation, that you fill not the equilibrium composition, slightly different, and then you will have a supersaturation. But typically in solidification reactions, you give an undercooling and thereby you give C fill. And this is a guess value. It is essentially at the undercooled temperature, you give certain properties such that the Hessian of the free energy gets computed at the undercooled temperature, which gives you the right interfacial properties. OK, so all of these compositions can be derived from PyCalphate. So since you're installing already PyCalphate and you have the TDB, you can essentially derive this information in situ. And this is a rotation matrix, essentially telling you what is your phase rotation going to be. And I'm going to give a 45-degree rotation. I'm going to go in a diagonal. OK, these are the boundary conditions. I'm going to leave them as NBC, which is Neumann boundary condition, which is the same for all of them. So I'm going to use the same. And then I'm going to import a shape. So in the interest of, because you're doing it the first time, so I'm going to choose the filling. So there are different filling possibility. You can fill the cube, cylinder, ellipse, sphere. You can use a random cylinder, which will be a random filling of cylinders of different sizes, or a random sphere. So random cylinder, cube, ellipse are possibilities for 2D simulations, whereas sphere and random sphere are for 3D simulations. OK, so let's say I do add cylinder. It will give you prompt how you want a cylinder to look like. All right, so I'm going to put a cylinder right at the corner here. And because I'm doing a 2D simulation, the Z start and Zn have to be 0. OK, and I'll give a small radius 5 and save. OK, so that will print out this line over here, which essentially fills one cylinder at the corner. In principle, one can keep repeating this activity and it will print multiple lines. They will print multiple cylinders or fill multiple cylinders in the domain. Next. So then after this are model specific parameters, which means particular to the model I chose, I need to put in parameters. So I will choose grand potential over here. And OK, this is a flag. So as I was telling in the morning, these are question marks which tell you what you need to fill. So if you are unsure of what you need to do, you can just click on them or just point your arrow to them. They will tell you what these keys are all about. If you are still unclear, you can go to the manual, which is there on the repository. There will be a larger description of the keys. OK, so I'm going to do, these are flags for slightly optimal calculations of the system. So if you have a two component system, you can explicitly choose binary. Some of the matrix operations will be optimized. So there are ternary, dilute. So these are just for optimization flags for the particular system. If you do not give any of them, OK, it will do the typical, it will treat it as a multi-component system and do the multi-matrix operation, in which case it might be a slightly slower thing. OK, so I'm going to put the right format as why is this? So if this is right HDF5.1, I'm going to use HDF5. Then this gets overwritten. It doesn't matter what I put in over here. And so there are different file formats you will see in the solvers. You have ASCII, binary, and you have HDF5. HDF5 is a parallel file writing format, which essentially tells you that you have one single file. And depending on the number of workers that you have, each worker is assigned to write a particular chunk of the file, data in the file. So it will be pre-assigned which chunk of data it will write on the in file, and it will just write that. So just one file will be created, and all workers will essentially be writing on that file simultaneously. OK, so this is possible with HDF5, and that's what is the most efficient format, particularly for if you launch it on multiple number of CPUs. OK, this is also the reason you required that HDF5 dependency that you loaded in the morning. OK, this track progress key allows you to print out on the screen frequently, how frequently you want. So this tells you that after every 10 steps, you will print out information. You can change this number to 100 or as the case may be, whatever you want to choose. These are again parameters, so you can read what these parameters are. This is a parameter that scales the interface width. These are taus, which are to the related to the interfacial mobility, but these are not used for the diffusion control simulation, they're internally calculated. OK, so whatever value you give over here, these are not going to be used. This feature will be added in the future release, where if you give a value over here, it will override the internal calculation, and that feature we will put in later. But presently, it is essentially doing diffusion controlled calculation, which essentially means it is that sweet tau or the sweet value of tau which gives you diffusion control or no interface kinetics in the system. That means the apparent interface coefficient in the solidification problem will be 0. OK. Apart from that, there is the function anisotropy. If it's 1, you are doing anisotropic simulation, so you're doing a 1. If it's 0, you do isotropic. All right. So let's do this. It's just to start cases, then you will get. So if you do this, these guys don't get ridden. This is the potential of 1 corresponds to an obstacle potential. An obstacle potential is something where you do not have derivatives, so it is not differentiable at the equilibrium points. OK, but as people have shown, this is not a big problem. Differentiability is not a necessary condition for a stable interface. OK, so you can actually have non-differentiable functions still giving you stable interface which move. So I'm going to use function W1. This is the equilibrium temperature. This is the filling temperature, which means the equilibrium temperature corresponds to the temperature of the alloy composition that you have taken. This is H70 as I told you. 857 is the temperature which you are filling your temperature and the temperature that you are going to consider. So therefore you have an undercooling of 13 Kelvin in the system. OK, this is not going to be read. OK, let's see why is it going to be read. Let's go there. Isothermal, I'm going to do yes. If I do yes, those keys will not be read. OK, temperature gradient cannot be will be pumped out. So shift is a key for doing shifting simulation. That means in the morning I was showing right there where the simulation was shifting as a function of as the simulation is moving forward. If this is on, you enable that feature. Otherwise, if it's 0, it's shut off. I can choose to have noise or I can remove noise. So I have put 0 here. And write composition is a key I have chosen so that you can write both composition and chemical potential at the same time. Right. So now I'm going to write down this as the isotropic because I have to put function anisotropy 0, and I'm going to do aluminium zinc, and I'm going to write this as OK, and I'm going to write this as OK. Let's generate files. So it will open a folder behind me. And I can create a folder here. For example, I'll create a folder here. I'm doing isotropic. Isotropic aluminium zinc. So it'll create that. And then I will open in this the 2 files that I have created. So I'll do OK. OK, and then I will run. So the first time you run, it will take a bit of time because PyCalFed runs in the background to generate the thermodynamic information that you need for the solvers. So this will take about 1 or 2 minutes. So these are the functional forms that are getting calculated using SymPy. They get written into the TDBs folder in the solver. The code gets compiled again, and then you start to run. OK, so this is now running. I have run it for 20,000 steps in a small domain, so it should happen quickly. Let's see. So these get written in the folder, so you can actually navigate to that folder and check what is happening. OK, so we will do that. So OK, so we are going here. This is the folder we created. There's a data folder over here. OK, so we'll open. OK, so you see there are files getting written down over here, which are H5 files. Now there is a particular procedure we will be doing in the next few minutes to actually convert these files into something that can be read easily. So you can follow them. So I've given 20,000 steps. It should run very quickly. Okay, just a few more seconds. Okay, so it would have finished. So, so you can check that it has finished. You see it has finished. So I can in principle close this terminal. And now to view it, what you have to do is to go to this MicroSim tool. Because these are H5 files, you have to convert them into VTK, all right? Because the VTKs are the only readers possible to read in Python. So you go to the navigate to the file where they are. So you are here. The data is here. Now first you have to choose an in file. So your in file is here. Open. Then you need to load the data, which is again going to the same place. So this is what you need to just choose once. It will load, and we have run from 0 to 20,000. So you can choose the the files that you want to recreate, and then convert. So this will open a box, convert, and essentially go back. So it converts to TDK and closes. So then you can close this. And then what you need to do is to import the in file again to view it. So let's go here. Import. And then import VTK. Okay, the data itself. So you see now VTK files are there. Choose the first file, so it will open. And then you can play. Okay, so you see because of the boundary conditions, it is sort of growing in a shape which is because of the, this is coming because of the shape that we have given. So now what we need to do is to put in isotropic, anisotropy in the system and check what happens. Okay. So let's go back to the, oh, we closed the in file. Oh, we closed the in file. So we can actually go back and do the, we can import the in file again. Okay. Where was the? Let's take this in file itself and modify. And all we are going to do is to convert the parameters. Where is this? Material parameters, or rather model specific parameters. So we'll go to the model specific parameters and change the anisotropy to 1. Okay. All right. So let's go there. All things are same. So we will do so. And you can generate in files. It will again similarly tell you, but this time what we will do, we will create another folder. Okay. Okay, open. Okay, so now it asks for all values in the rotation matrix because the that is not there in the previous case. It was isotropic, so rotation matrix was not required. So we have to go back and check the material parameters which are there in the rotation matrix. Okay, so we need to put in this value, which is the 0, 1 interface. So I've given a 45-degree rotation. So this gets written over here. And I will import the same shape that was there before. So this one. Yep. And I'll go next, 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 and try to generate files. Now that I have created a folder, it will try to do there, and we'll fill the file. Okay. I'll try to do the same thing. So now it runs faster because the Python files are running quicker. Okay, so now you will see something else. Well, hopefully something else. So again, you can go back and follow the same stuff. So you need to navigate to that folder. I'm doing that. So there's a folder here, anisotropic ALZN. So I'm going to go there. And you see the data folder there. And you see files are getting written now. Swapnil, time. What's the time in the what's the time in the brochure? So you see it's running. We'll wait until 20,000. Okay, let's go there. This must be finished. So you see on the right hand side, it's finished. So we can essentially, you can do it earlier as well without finishing, but I'm just for completion's sake doing it out. So you can again navigate to the folder. You can do the input file that is there. Locate the data. And follow the same type of thing that you did before and convert. So this converts, you can close, then you can go and import. Well, before you import VTK, you need to import the in file. You need to go here, input the in file, and then import the VTK. So we can try to navigate to the data now. Open the data folder. And now you see a different evolution. All right. So that's because of the anisotropy that you have given and it's rotated. Right. So this is what we can do quickly. As you see, we have done several things. Now the other example I want to show you quickly is a you take so if you go back and look at the phase diagram. So let's look at the phase. Where is this? If you look at the phase diagram, yes, here. So I'll blow it up. You see there's a eutectic in this phase diagram over here. So we were here. Now we'll do something here. OK, so let's try to do a eutectic problem in the same system after doing this. So let's do that. Let's go back. You can actually close this. You can go back and you can go back here and you can say I want to import new in file. OK, so this will just you can start the process again with a new in file. So let's say I want to do eutectic. All right. So I will import this in file. This is also there in the example in files I've shared with you. OK. Open. OK, and it's asked you some things which you will correct. All right. So first, it's going to be in a setup where things are going to grow in one direction. So I have biased the domain such that there is elongation in one direction. All right. So you have 50 in this way and 100 here. So that things are going in one direction. All right. Discretization in space and time, I'm going to keep it as they are there in the in file. The number of change, so phase names are going to be alpha, beta, and liquid, right? You can give different names if you want. These are proxy names, so they can be anything, all right? The component names are the same, aluminum and zinc. Then you go to next. So I'm going to run for smaller time. 20,000. I'm going to save often. And I'm not going to restart the simulation. So I'm going to start here. Now the equilibrium compositions, again, they follow the same strategy as before. They are going to be read in from the as the equilibrium compositions at the eutectic temperature, because that's the relevant equilibrium temperature we are talking about. So C equilibrium and C fill I'm going to give as the same. They are getting filled at the equilibrium temperature. And then I'm going to undercool the system such that the system is out of equilibrium and it grows, right? So, and C gas is again at that undercooled temperature. What are the phase compositions? So what are these values? They are there in the manual. So I will go into that can be read out. OK, next. OK, what is it asking for? Next. OK, so there is something missing over here. That's why it doesn't let me go ahead. Beta is there. So liquid doesn't have properties. That's why it will not allow me to go to gamma. OK, so this is something that you need to take care. All properties have to be put in such that it can go ahead. OK, so the diffusivities alpha and beta are 0 because they are solids. Liquid needs to have a different diffusivity. So I'm going to use 1e minus 9. And if you have missed what I did here, I'll use the liquid property. I clicked on this button, same as previous, which populated these quantities from the previous file. OK, now these are unrealistic, but it is just because liquid, these properties are not going to be used for this specific simulation. You can fill in any number right now, but in future, when we do solid state phase transformation, these numbers are going to be critical. So you need to modify them accordingly. OK, so I'm going to fill in 1e minus 9 as I did before, because typically now I can go with gamma. And again, you can go to each one of them. It will tell you which interface you're filling up. So 0.1, 0.1, 0.1, for example, are now filled up with all interfacial energies are the same. Then again, now here I'm choosing function F3 and I'm using thermodynamic phases. You see, I'm 3 thermodynamic phases are there because at the eutectic system, you have 3 phases. You have FCC A1. So you can see over here, FCC A1, HCP A3 and liquid. OK, so these are the thermodynamic phases. I'm using the same TDB, so the same in TDB exists. And the phase map now is for alpha, beta, liquid. That was the proxy phase name that you gave before. So you have FCC, HCP and liquid that stands over here. So that is essentially the phase map that we are talking about. So now alpha is associated to a thermodynamic phase, beta is associated to a thermodynamic phase, gamma, the liquid is also associated to a thermodynamic phase. What I mean is these names are there in the TDB. So these are the thermodynamic phase names that the system will associate with. OK, so once you have given this information, you are ready for doing stuff. You can go next. I'm going to use periodic boundary conditions here for the x direction, which is these two guys. I'm going to use x direction periodic because I'm going to use do a filling which is going to mimic alpha, beta, alpha, beta, alpha, beta type of filling. And I'm going to have Neumann boundary conditions on these two ends, which is why this is Neumann on both these ends. OK. Next. So now I'm going to import shape. I'll see if OK, let's fill it up directly. So let's fill a cube, add cube. OK. So add cube has 2 points, start point and end point to start with. So I'm going to start with 0, 0, 0, right? And the end point will be such that I'm filling a thickness of about 5 grid points. OK, that is 5 in the y direction. So and 25 in the, my thickness is 25. So 25, 0, 0. 25, 5, 5. Sorry. Let's give 10 just. So you see it writes down like this. Now I can add a cube because I need to fill 2 phases. OK, so I can add. Let me fill in 0, 0, 0. No, the starting point here is now the end point of the alpha phase, which is corner of the alpha phase. So this will be 25, 0, 0, and it will go on to 50, 10, 0. OK. So this is what it will get filled up. So you have, oh, sorry, this is, so you can go and edit. OK, let's say I do edit. So you can do beta and edit. OK, so the way to do that is to delete this because we have filled wrongly. We have to fill beta. So add 25, 0, 0 to 50, 10, 0. OK, so you have filled one phase with cube 25 until 2510, and then cube for phase 1. So this first is the phase index 25, 0 to 50, 10, 0. So you'll see what the shape looks like in a few moments. Next. So now we go into model specific parameters. Shift is 1. So I'm going to do a moving boundary simulation, and I'm going to shift until the interface reaches 30 grid points in the growth direction, right? So it tells me it needs 3 values for it. Okay, why? Because there are 3 phases, all right, or 3 interphases. So you have alpha, beta, beta, gamma, alpha, delta. So the 3 interfaces, it asks me for 3 values. Similarly, there will be 3 values for the DAB. And although there is no anisotropy, it's asking this. This is a feature which will be removed in the next point, but yeah, presently it's asking for a sanity check. OK, so now I will create this as input eutectic, and this will be filling eutectic, and I will do output eutectic. OK, so I'll generate in file. So here I will make another folder, which will be eutectic aluminum zinc. Create, and I'll open this. So it will get created over here, and then I'll run. So you see they are running. And again, as before, we can go back and check what is happening. So we were doing it here. So you see a new folder is getting created, eutectic aluminum zinc. So CD data, right? So you see these files are getting, and there is a new file that gets written down, which is shift.dat. This keeps a record of how much time you have shifted. This is necessary, so I'll just open this. This essentially tells that how many times you are going to shift in the simulation. The reason this is important is because when you want to recreate that entire simulation, because this is a moving simulation, you would like to recreate this simulation into a continuous one later on, right? So that you know how much time it has moved. To recreate that information, you need to put in that value, right? No, this is not happening appropriately. Okay, we'll have a look. I think there is something which is not really happening as it should, but anyway, it's okay. We will see CD data. So the simulation is over. So we can go back and do the same thing that we did before. H5 VTK. You need to locate this first. You take aluminum zinc. Input you take. Then look at this. Convert. So it's converted. Now we go back, import in file. Okay, import VTK. Okay. So you see it's growing, but it's growing in a slower pace because of the undercooling that we have given. So both phases will essentially, you can see both phases, and they will evolve such that they evolve into something which is a continuous thing. So the simulation, how it looks, is something after it runs long enough would be something that will evolve to something that I showed you in the morning. So I will just navigate to that file to basically show you what happens. So for example, I can do that over here. And I'll open it in ParaView. So just for convenience, I've kept it stored already because that runs longer than what will be possible here. So I'll open ParaView for moving it. The same in file. So what you should get is something that will be evident here. So the same filling. So I'll play. So this is what will happen. Okay. So this will what will happen. You can plot the different phases. So alpha, beta, and you can plot the composition field. Okay, and you can also plot the mu field. The mu field is less beautiful, and this is because there is no solid diffusivity. Okay, so the mu profile cannot will have things like this where the composition does not diffuse. So this is less evident over here, but it's more evident in the mu profile. So you can also convert this using some to see it as a phase map. So let's say because these phases are individually visible, so one can do a trick which I will show you to show them together. So you can use the calculator field in here, apply, create a field which is phase, okay, and associate a level set for each of the values. So I'm going to do 1 star alpha plus 2 star beta plus 3 star liquid, and I'm going to apply. Okay, and it will create a field for me where the 3 phases are separately visible. So you can then use the same information. So this is run long enough. This is run over 250,000 steps. What we have run presently is just 20,000. So it will reach this stage if you run it long enough, the same in file that we have created. Okay. Okay, so that's something. Similarly, you can do stuff. So we'll go back and do one more with a precipitation in file. Okay, so let's go back and do a new in file. How much time do I have? 15 minutes. Okay, let's quickly do it. So generate new in file. Now I'm going to choose a not generate. Sorry, go back. import new file. I will go and choose a precipitation in file. All right. So tutorial runs. I have stored this in file already. So TDB new ppt. Okay. So this is a small simulation. I'm going to record all of this. Phases are going to be, these are the same alpha. Okay, so you see the phase names over here are alpha and liquid. What I will change them to is beta, because typically I'm doing a precipitation problem. All right, save. So component names are aluminum and zinc, so I don't want to change them. This I will change it to 20,000. I'm going to save 10,000. Next, and these are again. Now this is a situation where I'm precipitating. So I'll go back to the phase diagram one more time. What I'm doing is I'm precipitating. So this end of the phase diagram is FCC A1. This end is HCP A3. So I'm going to precipitate HCP phase out of the FCC solution. Okay. So what I will do is I will take this as the equilibrium temperature 500 Kelvin, and I'm going to give an undercooling. So now I'm super saturated. So I will start to precipitate HCP out of FCC. Okay. So this is the situation I'm going to model. So these are the compositions corresponding to the equilibrium compositions at 500. Okay. So gamma 12 is the only interfacial energy because there's one. Functional properties, I'm going to use 3. There are 2 thermodynamic phases, FCC and HCP. Okay, HCP, FCC. And since my FCC is the matrix phase, I have put it as the last phase. Okay, so FCC is the matrix phase, HCP is the precipitate that comes out of the matrix phase, and this is the same TDB file. Okay, now so these are Neumann boundary conditions. I'm going to use Neumann everywhere. And here I'm going to use a new filling function. I'm going to fill the random cylinder. Okay, I'm going to put random cylinders. So I'm going to choose a precipitate size, which will hopefully grow. So let's do 20. Volume fraction, I'm going to choose very small. Shielding distance as 3. And so shielding distance is essentially what factor of the radius that you want separating with the precipitates that you put in. And what is spread essentially tells you R plus delta R, what is the spread in the distribution of R. So I will give it as 0.1. Okay, so this fills in a new key, cylinder random, in the filling.in file. Okay, then I will go into this model. There's no shift here because it's a precipitation simulation. And I'll change these names. Okay. All right. And I don't remember filling the temperature, so I will just go to material properties once to check out. Oh, there has to be coming. No, so it has to be coming in model parameters. Just let me go and check temperature once. Why is it not coming? Temperature is 450, so I'm cooling 50 Kelvin. All right. Equilibrium temperature is 500. I'm cooling 50 Kelvin to get this. Okay, so I will generate files. Again, same strategy. I will create a folder. Precipitation aluminum zinc, create and open. So, and I'll run. So you start to see running. Okay. Now you see alpha and beta, they are the only 2 phases, and aluminum, okay, which is the phase component that I'm solving for. So let's go and check what is happening in the folders. So let's go here. Okay. So we'll just wait till just complete. Okay, so we are done. So we'll just go back and do the same thing that we did before. We'll just close this and MicroSim tool. So we can close this guy. We'll start a new one. We'll just go here. Okay. Oh, sorry. This has to be first converted to VTK. Sorry, I lost my own thing. Locate data. So choose the H5, open, and these things remain the same. So convert. This gets converted, and then you basically do the same thing before. This is the single file. You're going here. Choose the VTK. Okay. So as it happens, the filling that we gave, it just filled one because the properties were such that you filled just one. Right. That can happen. Just choose a larger domain and it will choose the right stuff. But yeah, that's because of the filling that we did. Okay, so you can check what happened to it, and it grows slowly. Well, it's a precipitation, so it's and you can do several things. You can do area measurement, precipitate size, and you can plot with time, for example. Well, it's too small to plot, so yeah. So there are several things that you can do. There's just one precipitate count here, so doesn't make too much sense. But yeah, you can essentially calculate everything to do with precipitates in this particular part of the problem. All right, so that's essentially a reasonable demo of what one can do with OpenTDBs. And in the following session, I will do the same with encrypted DBs to give you a demo of what will happen. So now I'll just leave it for questions. So if anybody has questions, please go ahead. Swapnil, any question? No. Okay. Questions yet? You can drop a message. You can connect and ask me the last question. Okay. Any questions from the audience here? So anyone pretty well trying to do it with me along? Anyway, it's recorded, no, fully?
Yeah.
Okay, the recording is there, so one can essentially follow that and quickly. The example in files are all in the repository. I can guide you there. So let's open this. So let's go here. So if you navigate to this is the grand potential finite difference 2D MPI. You will find in files over here. You'll get a whole bunch of in files. Okay, you can essentially choose the ones I chose over here for the thermodynamics. So input underscore TDB, all with TDB ones are TDB in files. That means they run with real alloys. So so TDB new.in is the one that we modified. New aluminum zinc ppt.in is what we used. Aluminum zinc eutectic is also what we used. All right. So all of these things you can explore, and what I'll be showing further are these 3 encrypted ones, which will be in the next session. Okay. Okay, very good. Okay, then if no questions, we can break for lunch quickly and then